All right, hell yeah. So we're going to go over trigonometry, and I for sure spelled it wrong. I apologize about that. Maybe I didn't, but it just looks really funny. Anyway, a subscriber was like, hey, is there easy problems to learn about trigonometry? And so I'm going to go over the basics of trigonometry that I like. You know what I mean? I don't think you need to know a ton about trigonometry, and almost less is more. You know what I mean? I think what's overlooked is Pythagorean's theorem, because in trigonometry, heck yeah, you're trying to turn everything into right triangles. It's a very useful concept, because if we do have a right triangle, we do have something that's longer. Like, obviously, this is always going to be longer, and I never think of it as the hypotenuse, because that's like middle school, where you're just like, hey, what's the sine of the angle? Well, isn't that opposite over hypotenuse? I even have to pause every time I kind of do this method. When you get into engineering, like this is your vector. You know what I mean? You're like, hey, I'm putting like 100 pounds of force that way. I want to know its component this way and upward. You know what I mean? So, and I know that these components are always less. So that's kind of my go-to, is that, you know what I mean? We have an angle here. And one of these components is the sine, and the other is the cosine. So, and then keep that in mind. And the main thing that I don't think you can reiterate enough is that you have, because I think what also gets confusing is you have sine, cosine, and tangent, kind of as your gold standard. Hey, there's three things. It seems like they're all the same. Hell no. This one, you know what I mean, is totally different. Sine and cosine, these are percentages of this total distance. So if I even say, like right now, this total distance is 10, you know what I mean, just use your guessing skills to be like, hey, this length is 10, whatever's, this looks like 8, this looks like 7, you know what I mean, this looks like, yeah, you know, and if I guessed 8 and 7, I mean, hey, I'm really friggin' close. And we'll get into, because the other aspect of that is like, yeah, it's good to know a few of these values. You know what I mean? Hey, this looks like about a 45-degree angle. If this is 45, what is the sine of 45? What is the cosine of 45? Okay, so then the next thing is, I guess it is good to know kind of like the 8th grade method of like, hey, what is sine theta and what is cosine theta? Cosine theta is the adjacent over the hypotenuse. And still, those are some things that you still have to memorize, you know what I mean? I think this is just burned into everyone's brain as like sine is opposite over hypotenuse. Well, cool. If that's what you can remember, then just know that cosine isn't the opposite over the hypotenuse. It's the adjacent over the hypotenuse. And just know that it can't be anything else, because the hypotenuse at the end of the day is the bigger number, and then you're gonna this adjacent part or this opposite part, these are the smaller numbers. You know, so even right there, you're gonna have the opposite is a smaller number, hypotenuse is bigger number. So that's my rundown on sines and cosines. And then, I don't know, I've just developed, because it's just like one of those things that, what's the fastest way? And this is, put a little sunshine on this, and hell yeah, I call this the sun is shining on the sinin part. Just instantly, this is going to be the sine theta component. And even when I write it, you know what I mean? Hey, I just wrote sine theta. What the hell does that even mean? Well, the second thing that I go over is that sines and cosines are percentages between 0 to 100%. But basically, they're numbers between 0 and 1. If you're doing geometry, that side of trigonometry, hell yeah, these are always going to be positive values, and they're always going to be between 0 and 1. Where we're trying to actually find this representation, the percentage of this distance compared to the larger one, the hypotenuse, you know what I mean? Okay, so these are going to be numbers between 0 and 1. They're fractions of that whole. And cool. And so just right there, if I see the sign, my brain instantly knows that this is a percentage. If I take that number times 100%, then I get a percentage of this actual thing that I'm analyzing. Maybe a vector or a force, a force in that direction. Okay. And then the cosine is the same thing. This component in this direction, if I say this is the cosine of the angle, cool. If I just write this, I know it's a number between 0 and 1. Well, let's just say it's 0.7. And now does this make sense? Because if I go 0.7 times 100%, I see that it's 70%. Hey, 7 is 70% of 10. You know what I mean? So the sine of this angle would be 0.8. That's the representation of a number between 0 and 1. Times 100 is going to be 80%. And that's going to tell you basically that component. We know that this side always has to be less than the hypotenuse. If your angle's not, if you have a triangle. I mean, like obviously if you don't have a triangle and you bring this angle down to 0, well, your hypotenuse is 10, this height is 0, and then this cosine length is 10. You know what I mean? But you don't have a triangle there. Same thing if you went up to 90. If you took that thing straight up to 90, well, now you have all the sun is shining on the 10, and then there's no cosine part. Cosine part's 0. You know what I mean? So, you know, those are the extreme cases that you're probably not going to use if you're doing like geometry. And I think trigonometry is good to use using geometry. You know, because that's the first. You're using trigonometry to you know, all your values are positive. Hey, you have a distance there, a distance there. You know, nothing is a negative number. So cool. All right, so then what's the next thing? Well, I guess the next thing is like, well, how did you get from 80% into 8? You know, because the main equation that you're going to be using as an engineer is like, hell yeah, you know that this is your vector or whatever. It's got a magnitude of 10. I just want to know what the sine part is. And so basically I'm going to take that larger number and then multiply it by the fraction. And we know that these are the fractions. It's the fraction of that larger number. So if I go larger number times sine theta, hell yeah, that is going to be that vertical component, and that's going to be 8. So if I take 10 sine theta is equal to 8, I just said from our representation sine theta is 0.8, so 10 times 0.8 is equal to 8. And see, I didn't even have to, you know, have a value for this angle. I'm just visually representing this. Okay, so that's going to be number one. I think drilling in sines and cosines, because I even know, I just know this for a fact that you get so much knowledge that you forget that the basics are where you need to be spending like 90% of your time. Like watching some of these like MIT, you know, professors, and you can just kind of tell the students are just like, you know, the professor does something and then throw a cosine theta up there, and I'm sure just a lot of the times the students are like, okay, there's a cosine there, but at the end of the day, I really don't know what that means. You know what I mean? But now you do. It's going to be, at least, who cares what component it is? Because even if I draw my triangle different, and I say, hey, same triangle, and I'm saying this is theta. Well, cool. This is the sun is shining. Guess what? This is the sine component. And then this is the cosine component. So even if this is still 8 and this is still 7, this distance right here and this distance right here, and this is 10, now I'm saying the sine of that angle is 0.7. The cosine of that angle is 0.8. So look at that. The cosine of this angle was 0.8. And then that was equal to the sine of that angle. You know what I mean? So that's gonna bring up another great thing that you should do for all problems, because having a triangle that looks almost symmetric is like the worst thing ever, especially if you're doing like a ramp problem. You know what I mean? You'll have a ramp that looks like that, and then you'll start drawing things in like, hey, this is gravity, and then hey, this is that angle. Wait, is this that angle? You know what I mean? So then the second thing to do is be like, nah, don't make a ramp that's pretty close to 45 or even like a 30-degree angle. Just really slacken it out, because then, let's say we have this ramp and we're going to do that same thing. We're going to put a block on it. I mean, in physics, you do this all the time, and now you're going to have a weight that's just going to be downward. And so we're saying, hey, this is the angle here. So now you're using that geometry to kind of just like, well, I know that we're going to do like, hey, this is perpendicular, parallel to the plane, and then this is perpendicular. And then so how would I prove that like this angle is that angle? Well, I think we just did it. Like, just drawing it like this, that angle looks like that angle. You know what I mean? So check mark on reality. But if it looks like this, I have no idea. And because and that brings up the second point. So even if we have that really shallow triangle, anytime I get a triangle, I'm gonna say, hey, one of the angles is theta, and then automatically I'm gonna go for the other angle and say that's phi. You know what I mean? And it's good to get used to different characters. And this phi does come up, but when it does come up, it might throw you for a mental loop. You're like, I don't want to use a different character for angle. Angle's always theta or something. But if you represent it like this, you know what I mean? This is 90, and now, you know what I mean? All the basics from like 8th grade come out. Like, hey, 180 degrees has to be the angle of a triangle. And so we have 90, that's the plus phi plus theta. And now you can see 90 degrees has to be phi plus theta. I'm sorry I didn't write this as theta. And then from here, you can say, hey, if this angle is like 20 degrees, well, just from what I know that this has to be 90, or 70, you know what I mean? 70 plus 20 is 90, and now we're good to go. So we're going to go 20 degrees plus, I'm sorry, if you wanted to figure out, you know what I mean, do a little equation, and this is 90 minus theta, that's 90 minus 20 degrees, and you have phi. All right, so hell yeah. So now these are the building blocks, and I at least within the first 10 minutes, I should have just said this right off the bat. You know, sines and cosines are everything with triangles, but the one that you just can never forget is Pythagorean's theorem. So we're going to do that same triangle. You know what I mean? We're going to have 10, 8, and 7 or whatever. And you just, like, anytime you're doing the second sine comes out, just friggin' write Pythagorean's theorem. A squared plus b squared is equal to c squared. Because your mind goes like, oh, I must need to use trigonometry. I must need to use sines and cosines of angles and tangents, when a lot of problems can just be like, nah, you can get what you need just by using Pythagorean's theorem. And it's a full other equation that's a kind of a check on reality, and sometimes you know, if you don't have Pythagorean's theorem, you're not going to actually solve the problem. You know what I mean? So and that's just going to say that, hey, 7 squared plus 8 squared is equal to 10 squared. Now we just guessed this, you know what I mean? We just made a triangle that was 8 and 7, and we just did this one. Hey, we drew this one and we thought that looked like 8, this looked like 7, this looked like 10. But you know, if you have 3 sides, if you have 2 sides of a right triangle, you've already determined the third side. So just my guesses here have to be wrong, because unless we got a 3, 4, 5 triangle, they ain't going to be whole numbers. So let's do this. This is 49 plus 64, and this is going to be 100. Well, we're pretty close. You know, I mean, we're about 15 off. You know, this is about 100, and 113 is equal to 100, and then square root both sides. So you know. So yeah, we were definitely off. If this is 8 squared plus 7 squared square root that, this would be about 10.6. You know what I mean? And if this was 10, and we're saying that, which one are we more accurate on? I think I'm more accurate that that's 8. So then we would do 10 squared. So, and the other thing, Pythagorean's theorem, the next one is like, you know, this is what I kind of teach in engineering, is like, hey, anytime that you get an equation, you know, it probably has 3 things in it. You know what I mean? That's very typical for an equation to have 3 things. Doesn't need to have 3 things. But if you have 3 things, well, usually it does. Actually, no, that's like a fundamental, because like, check this out. Like, let's say you have, you know, I don't know, f equals ma, y is equal to mx plus b, never mind on that. But yeah, I guess the one that I use is acceleration is change in velocity, change in time. You got three things here, you know what I mean? And then you got velocity is change in position, change in time. You got three things here. So you can rearrange these equations and get three separate equations. So even right here, let's say I want to just solve for, one of these. I just want to solve for what... I thought this was pretty accurate. I don't think I know what a is, so I'm just going to solve for a. A squared is c squared minus b squared. You know what I mean? And if I wanted to get an equation for a, we're going to do c squared minus b squared. Cool. And let's at least do that. So we're going to go 10 squared minus 8 squared. Square root that, and we should get 6. You know what I mean? If this is 8, yeah, that's going to be the classic. This is the 3, 4, 5 triangle. You know, this should be 6, and this is 6, 8, 10, 3, 4, 5. You know, it's 3, 4, 5 triangle, and we just solve for that. Okay, and so yeah, and that kind of leads into Pythagorean's theorem. This is why a lot of stuff with sines and cosines look like, whoa, the square root of something squared minus something squared comes up a lot. Or something squared plus something squared, for that side. It definitely comes up on a lot in a lot of equations. All right, so, but now, I mean, we just want to kind of know the general basics. And so now we're going to introduce tangent. Now, for tangent, I just think you probably should just know kind of the 8th grade motto that, well, I don't know, because tangent from 8th grade is opposite over adjacent. And I think actually that's not the way I would remember tangent. From the engineering perspective, tangent of the angle for me is just sine theta divided by cosine theta. And this is a visual representation that the tangent of this angle is going to be the sine part divided by the cosine part. And it's always, and then go back to 8th grade, it's the opposite over adjacent. You know what I mean? It's always, if the sun is shining, the tangent is always the sine part divided by the cosine part. If this is the we're finding the tangent of the angle, it's always the opposite part divided by the adjacent part. Now, if your angle's up here, the tangent of this angle is the opposite over adjacent. Or it's the tangent of that angle is the sun is shining divided by the other side, the cosine part. Cool. And and now I'm gonna actually we're gonna finish this video in a cool way. We're gonna finish it with tangent theta is equal to sine theta divided by cosine theta. And now this brings up a lot of different things with like, hey, what the hell is cosecant theta? Sometimes I don't even know if I wrote that right. And then we have secant theta. But my brother did said a pretty good axiom. We know, and then, you might know cotangent the easiest. You're like, oh, well, that's easy. Cotangent is just, well, what the hell is cotangent? This is messing with my mind because you have two different things. Cotangent is just, isn't it just 1 divided by tangent? Yes. Okay, holy hell. But yeah, cotangent is just 1 divided by tangent. So what we're getting into is like you need to know that there's a relationship with tangent. It's the sine divided by the cosine. But any time that you have an equation with tangent in it, just replace it with sine and cosine because now you know what those parameters are. And so yeah, we're going to do a little example about that. It's just like, well, yeah, because now if I do cotangent, well, hey, let's just replace this tangent with this equation, sine over cosine. This is just going to be sine theta divided by cosine theta. And now, if you're doing problems, hey, look at this. We have sines and cosines. We know where those come from. They're fractions of a hypotenuse. They're a relationship between, this sine theta is the fractional component of that hypotenuse. You know, if this is your angle, here's the opposite, and it's the fractional component of that side of that right triangle compared to the hypotenuse. You know what I mean? So even when you see this, like, hey, you got two of those relationships, you're dividing them. Who cares why you're dividing them? That just comes out in the nature of using those. But at the basis, you want to have just that firm understanding of what sines and cosines are. Okay, so now we did it. We turned cosine, so now we know that cotangent of that angle is just cosine theta over sine theta. So anywhere where you have a problem that has cotangent in it, just replace it with that. And so here's how you can remember, hey, we know that these are related to 1 divided by sine theta or 1 divided by cosine theta. We just don't know which one. And so we take the word cosine, and we have the C in the beginning, S at the end. And when we do 1 over cosine theta, well, that's kind of like a little upside down or twisty, you know what I mean? So we're just going to flip-flop those letters, and we'll have S over here, C over there, and then we'll just have the vowel in the middle. So that's just the fastest way to know that, hey, I know I have 1 over cosine. You know what I mean? Hey, how do I convert that to whatever I'm supposed to convert it to? And that would be secant theta. But usually, why the hell would you even do that? Just keep it in this form. Visually, it's representative of something. You know now what cosine is. And sure, 1 divided by it, you know, the problem just comes out that way. But sure, there's going to be problems in books where you just see secant theta. And you're like, nah, thanks. And moving on to the next problem. But now you can be like, oh, well, I'm just going to convert that to 1 over cosine theta, and now my brain's on a vacation. You know what I mean? We kind of know what the hell's going on. And it's even worse when you have, like, you know what I mean, a big equation, and then you're, like, dividing by secant theta. It's just like, why the hell would you have done that? You know what I mean? Because if I'm just going 1 over secant theta, well, what the hell is secant theta? That's going to be 1 divided by cosine theta. If this is the fraction, we're going to have 1. I'm just going to, instead of dividing by this fraction, I'm going to divide by the upside down of it. So cosine theta divided by 1. And heck yeah. So 1 over secant theta is just cosine theta. Now, so cool. No, and then that just must mean that cosecant theta is 1 over sine theta. You know what I mean? Just from that representative of, hey, these two are the same. I can't use that trick, so maybe I don't know what that is. So I come over here to secant, and yes, these two letters are different. I'm going to flip-flop them, and then I can see that this is cosine theta. Heck yeah. And and you could do it the other way around. If I have sine theta, obviously I'm not gonna have n and s. That doesn't give me anything. But if I have cosine theta and I want 1 divided by it, hell yeah, there's the c and there's the s. I'm gonna go s, c, and then put the vowel, and 1 divided by cosine theta is equal to secant. All right, so and that'll probably do it for kind of just the intro to trigonometry. But I haven't gone over a lot of Pythagorean theorem problems, but just, oh man, anytime you're doing geometry, it's so fascinating that you can forget about the Pythagorean theorem. And even like right now, it's just like, how do you link the two? I said you're going to get a lot of things like this. It's because you're linking Pythagorean's theorem. So we'll do 2 things. We'll do this. So if I do have this angle, and I do know that this is the sine theta part, and this is the cosine theta part, and this is that fraction of the whole, and this length could be sine theta if this length is 1, you know what I mean? So that's where that comes from, you know what I mean? Hey, we have a number 1. That's why I don't like the unit triangle, because it'd be cooler if it was like 100. If we say this is 100, hell yeah. Then I know that this is, for our problem, well, now the problem's kind of flipped. Well, let's say this is 6 and this length is 8 now. And so we're going to get, 60%, or, yeah, so this would be 60. This looks like 80%. This would be 80. But if we do have that unit triangle with a 3, 4, 5, sine theta, cosine theta, this is 1, and this is our angle. And we know this is like a 3, 4, 5 triangle. Well, this is going to be 0.6, this is going to be 0.8, and I guess what I'm getting at is, how do we use Pythagorean's theorem here? Well, instead of using the 0.6 and 0.8, well, we can do that. Let's use Pythagorean's theorem. We know that 0.6 squared plus 0.8 squared is equal to 1 squared. Cool. You know what I mean? And we can do that in our calculator. 0.6 squared plus 0.8 squared is 1. Square root of 1 is 1. But we can also do the same thing with sine. So we can say sine theta. And I would do it like this until you get hella comfortable with writing, until you get really comfortable with writing it like that. This is sine squared theta. And this is how you say it, sine squared theta. But it's actually sine theta, whatever that value is, that fraction of a whole, in our case it's 0.6, and then square it. You know what I mean? So I like to write it like this, cosine theta squared, at least until I get the hang of it. And you can spend a lifetime writing it like this, and it'll just help your game so much better. Okay, so this is going to be equal to the hypotenuse squared, 1 squared. But this is where that relationship comes from. You see it all the time. Sine squared theta plus cosine squared theta is equal to 1. But I don't have to memorize this one. You know what I mean? We go back to the basics of what do I want to memorize? The fact that sine and cosines are a fraction of the hypotenuse, and the fact that we have Pythagorean's theorem. Just those two things are gold. Sure, if a tangent comes up, I want to know what the hell that relationship is, because it's going to be in problems, tangent theta. But I know if I do a problem, and that's what we're going to finish with, I don't have to even use tangent. I can just say it's going to be sine theta divided by cosine theta, and I never have to use tangent. And in actually our problem, it's actually a cotangent theta. And someone actually said, well, isn't the relationship between that what do you call it? A proportion of cotangent theta? And I just scratched my head, because I was just like, well, no, I think it's a proportion of cosine theta divided by sine theta. But obviously it was a cotangent. Or no, I just thought it was 1 over tangent. It was just like, no, it's a proportion of 1 divided by tangent. But we're all saying the same thing. And it's probably easier to just say, hey, leave it as cosine sine theta. So here is that, I'm going to throw some more time on the clock. Alright, and before I do this last example, I do want to say, sure, if you want to learn more about trigonometry, pick problems that have that representation. So this final example that we're going to do involves tangent, and actually 1 divided by tangent. So technically, we found a relationship with cotangent theta. You know what I mean? So we found a problem that involves cotangent theta. So that's what you should do. You know what I mean? You should be like, go look online and be like, hey, what's a problem that involves secant theta? What's a problem that involves cosecant theta, and why? You know what I mean? Why 1 divided by sine theta? And we can't end it there, because the most important thing about, so that's just from the geometry side. But then, this is sine theta, this is cosine theta, this is theta, and this is 1. So what we want to know from the calculus side, because we definitely have equations that involve sine and cosine, and so we want to know what those look like. You know what I mean? So I do, this is going to be great. I do my scale, and we go -1 to 1. So in this case, when we actually use sines and cosines, we can't neglect that it actually goes from -1 to 1. It fluctuates. Sines and cosines fluctuate between negative and 1. But from a geometric standpoint, you don't need to know that they're negative. You know what I mean? But to draw these, let's say I'm just drawing sine x. What I want to do is draw 3 equal things right here. Because why do I draw 3 equal things? I don't even know why. But it's because, then you have, I guess this is important too. A full circle is 360 degrees. But if we do this, and yeah, this is why like the unit circle sucks. Your mind melts. But anyway, so this is a circle of radius is equal to 1. Cool. That's the radius. This is the what you need to know is that take a string and then measure out that radius and then start draping the string around the circle, and you'll probably get to about there. Cool. Take that same string and then keep draping it around the circle, and you'll probably do something like this. You know what I mean? And this is a pretty good visual representation. We went 6 times around and we have just a little bit extra. And you know what I mean? And at the end of the day, this distance looks about 6 times that distance. And it's just so fascinating that if you asked anybody, if you had 6 times the radius, what would that equal? Well, it's the circumference. But you'll never see circumference is equal to 6 times the radius. But plenty of times you'll see that the circumference is 3 times the diameter. You know what I mean? I mean, close enough. You know what I mean? Pi, it's going to be 3.14, but who cares? It's just 3 times the diameter. But for whatever reason, knowing that the circumference is 6 times the radius, it just melts your mind. You're just like, I've never thought of that. You know what I mean? And it's not. It's 6.28 because it's, pi, it's 2 pi. You know what I mean? So the circumference of a circle is 2 pi times that radius. You know what I mean? So we have 6.28 times that radius of 1. And then we're going to have so in this, our circumference is 6.28. Cool. So, but now we know that, and what we call this, if we take the radius and drape it up to there, that angle is what we call 1 radian. So we're going to say, hey, that angle is 1 radian. And this is where I give the axioms of like, whoa, radians sound hella confusing, and even college kids forget to know what the hell's going on with radians. Even this definition gets so overlooked and should just be told to you every single day. That a radian is like, yeah, measure out the radius, drape a string around a circle, you'll get to there. That's 1 radian. And it's about 60 degrees, obviously, because there's 6 of those in 360. But you come up short, so it's actually like 57.4 degrees. That's 1 radian. All right, so, and then my axiom is, well, yeah, radian sounds hella confusing. So I'm going to say radian is I'm sorry. What I say is radians, that confusing thing, times the radius actually gives you something normal. And in this case, the angle in radians times the radius gives you arc length. You know what I mean? And we just proved it. So we have a radian of 1 radians, a radius of 1 whatever, meters, you know what I mean? And now we have an arc length of 1 meter. So if this is 1 meter, that's that arc length of 1 meter. Okay, all of this was just craziness to show that, whoa, like you have this is this is 1 radian to there. This is 2 radians. So this is approximately 3 radians, but it's actually 3.14 radians. Okay, so at 90 degrees, you have approximately 1.5 radians. And this is where no one even thinks that this is 1.5, and they should. Just, it's the same perspective that you should know that a circumference of the circle is just 6 times the radius. Like that's a game changer. It's a guesstimate, but it's like hella way simpler. Because, and then even this, you've probably never even seen that 90 degrees is about 1.5 radians. No, like it's told to you that this is pi divided by 2. And that just melts your mind because that's just 3.14 divided by 2. That's just 3 divided by 2. That's about 1.5. 0.14 divided by 2 is 0.07. Yeah, so now you're going to have 1.57, and who cares? Who cares about that 0.7 part? But this from 0 to 90 is where we live for that triangle. So you don't have to, like 3/4 of this circle is just who cares if you're doing geometry, in 3 dimensions. That's what I was saying. It's like we don't care about negative angles or angles that, you know, sweep down here or over there. We're just trying to be like, yeah, I see that. That's the angle, that's the triangle. And within this range, yeah, so my triangle can go from 0 radians to 1.5 radians. It can go from 0 to pi divided by 2 radians. So if it's 1.5, that was the whole roundabout way just to say, hey, there's 3 hashes here. You have 0.5 radians, you have 1 radian, and you have 1.5 radians. So there you go. It's best if you draw it like this compared to saying that this is, well, like this is pi divided by 2, you know what I mean? And then, well, what's a third of that? You know what I mean? If this was pi, this would be pi divided by 3, and this would be 2 pi divided by 3, but it's not. We have to divide by another 2. And then, so this is pi 6, and this is 2 pi 6. Or did I do that wrong? Yeah, this is pi divided by 3. Am I doing this wrong? See, that's where it was just so much easier to be like, oh, okay, if I have a circle and this is the radius, and if I go up to that radius, I go about there, it's about 60 degrees. I have 30 left over. Heck yeah, that's 1 radian, and this is a half a radian. So cool. So right here, I'm going to have 30 degrees, 60 degrees, and 90 degrees. You know what I mean? If I go up 1.5 radians, I'm right there. So yes, see how even actually getting these exact is crazy? So what's pi divided by 2 is 1.5. Pi divided by 2 multiplied by 1 divided by 3, that's going to be 0.5. So yes, pi divided by 2 multiplied by 1/3, that's pi divided by 6. That's what that is. And then if we had, and then if we doubled this, so we'd multiply it by 2, we'd get pi divided by 3. That's what that is. So yeah, I was right. Pi divided by 6, pi divided by 3. And this is pi divided by 2. But see how that just melts your mind? That is just nonsense to memorize it like that. Just 0.5, 1, and 1.5. And this brings up, I mean, yeah, this is so crazy because it's just the simplicity followed by simplicity. And now we're going to, I mean, the greatest axiom in physics or in trigonometry is just the fact that sine in radians, if you're doing sine of the angle in radians, is just equal to that number. So if I have sine of this number in radians, the answer is just that number for any angle between, and I'm just going to say 0 to 30 degrees, because we all know what 30 degrees is, you know what I mean? And you could say approximately up to 60. 0 to 60, who cares? You're still going to be hella accurate. And that's the crazy thing about what we're going to draw in this graph. Because if that is true, 0 to 30 and 0 to 60, then our graph looks like this. So we're going to go from 0 to 1, so 0 to 60. We're going to do a straight line. And what is it? This is 1, this is -1. So this is 0.5. So right here is where I'm going to draw the line from 0 to, and then do I need to kind of go over that? I think I do. So we're going to say sine of 0.5 radians is the same thing now. You know what 0.5 radians, you know what 1 radian is 60 degrees. So 0.5 radians is 30 degrees. And this is cool because now I'm going to bring up my method of what I memorize with sines and cosines. Obviously, sine 0 degrees is 0. Sine 30, this would be the second one to memorize. It's just 0.5. Like that's the easiest one. And then sine 45, you know what I mean? It's a little harder. I just think 007. So it's 0.707. Because if you think 007, like obviously it's not 0.007. That'd be ridiculous. And obviously it's not 0.7 because why would I even say 007? And so the only other combination that you could have would be like 0.707. And obviously it's not going to be 0.077 because we're already, it's got to be at least bigger than 0.5, you know what I mean? So all those different combinations drop out. I guess it's not 0.77 because why would, if it was 0.77, I would just say 0.77, you know what I mean? So there's an O in there. So thinking 007, like James Bond, I think you can get there. That's a really good way to memorize that. And then sine 60. Now this is an interesting one. I just think 85%. I apologize that there's no good way to memorize that one. But this could be 85%, or you're going to see in our example, it could be 100%, who cares? You know what I mean? And that's the most fascinating thing about sine 60. It's either 85% or who cares, it's 100%. And let's do a visual representation of that. If I have an angle of 60 degrees, which is pretty damn steep, 60 degrees, you know, that would be a hell of a slope skiing or doing anything. And I'm going to say, again, this is 10 inches. Well, what is this? I mean, it looks, I mean, I guess it's not 9, you know what I mean? Let's say you guessed low and it was 8, you know, that would be a fairly good guess. But let's say you did guess 9. And then if you guess 9, you know what I mean, hey, this is going to sweep into there. So that's the other thing. Anytime you have a triangle, you can just sweep it into there and be like, whoa, well, what is this? That looks about like 9. And in the end, who cares? It's about 10. You know what I mean? So you can say, even with the 60 degrees, this length is pretty much that length. And that's going to come up a lot in vectors, because if I'm pushing at an angle of, like, let's say this, you know what I mean? So this is my 60 degrees, and I'm pushing on a wall with 100 pounds. Like, what does the wall feel in that direction? I mean, 100 pounds, who cares? Just get on with the problem. So I do that a lot. And that's exactly what the graph shows. So it's cool to use some of these simplistic models, you know, with confidence to make your problems just so much easier. So we know this to be 866. You know what I mean? I don't know. I just memorized that there's a doubleness there. It's not 0.85. It's just a little bit bigger. But I don't know. I don't have any good way to remember that one except 85%, 100%. And I just memorized it to be 0.866. Maybe I play off the 007. The fact that you have that doubled up. And then sine 90. Sine 90 is 1. Cool. And then from our equation, you can find the opposites. You know, let's say I'm trying to find cosine 0. Well, that's just down there. That's just 1. And then the equation for that, again, if I'm saying that this is 30, this has to be 60. So what's the equation? I'm going to say there's theta, and I'm going to say, you know, this is already 90. So I just know that these two angles have to be equal to 90. You know, I don't have to go to 8th grade and say the whole triangle has to be equal to 180, because I already know we have a 90-degree angle. So I just know that the remaining two angles, whatever they are, have to be equal to 90. And I just chose one. So even just that, if I have a right triangle and I know one of the angles, I already know the other angle. So let's say this is phi. That's going to be 90 minus 30. So cool. So that's where we get cosine of 0 is just the sine of 90 minus 0. So that's going to be the sine of 90. What's the sine of 90? That's 1. So that's the way to memorize all these cosines. What's sine of 30? Well, let's do it the opposite. Let's say, what's cosine 60? I don't know what cosine 60 is, but I do know if I have an angle and I'm saying that this is 60, the sun is shining, here's the sine, so I want this. Then I'm going to go to the other angle, phi, and I'm going to say, hey, sine of phi is going to be exactly the cosine of, you know, it's going to be the same representation. So should I do that again? So if I have I don't know why I'm drawing my triangles backwards, but if I have this to be 60, I know this is the angle, the sun is shining. Here's the sine component. That means that this is the cosine component. This is cosine 60. If this is 1, that's the actual distance. If this is the hypotenuse, you just multiply it by the hypotenuse. Alright, had to take a little break. But I guess what we were going over was, what were we trying to find? Cosine 60? Hell yeah. So what is cosine? Well, it's that. And so what we're saying is, like, we'll just take the other angle, phi, and then, heck yeah, that's going to be sine of phi. So sweet. So cosine 60, and we're just going to say the hypotenuse is 1. So cosine 60 Well, it's just going to be the sine of whatever that angle is. And we know that if this is 60, this has to be 30 because both those have to equal 90. So cool. So cosine 60 is going to be the same thing as sine 30. You know what I mean? So it's kind of nice to do that in your head. And that's just one thing I would never memorize. If I'm saying that this is theta and then this is phi, I'm just going to say if I know theta, then maybe, I don't know, theta plus phi is equal to 90. Do anything, even going back to the 8th grade method of just like 180 is the triangle, that's going to be 90 plus theta plus phi, and then I know theta, so solve for phi. And so that's what we're doing. We're saying phi is 90 minus theta. You know what I mean? So that's something where you don't need to know that, hey, cosine theta is going to be sine of 90 minus theta. This equation is one of those is just like, don't memorize it. You know, that's dumb. Just know the basics and know that, sure, every time you do that, you know, scratch your head and be like, well, what is, you know, cosine 60? Like, you know, how do I get from cosine 60 to a sine of some number? You know, sine of 30. But now it's really easy. Cosine 30, we know that is 0.5, and then we know cosine 60 is 0.5. Alright, and then same thing for cosine 30 is going to be the same thing as sine 90 minus 30. If you want to memorize that, I just don't do that. But it's just, hey, sine of 60, and that's going to be 0.866. So cool. Cosine of 30, you know what I mean, is going to be 0.866 if we take the cosine of 30. Alright, so those two rows are really good to memorize. And then we're going to do one more thing before we actually draw that graph in. Is like, hey, like, isn't tangent of the angle, isn't that the sine component divided by the cosine component? So let's do this graph. You know what I mean? If we have the angle of 0, 30, 45, 60, and 90, here's the sine, here's the cosine, and what we want to know is maybe the tangent component. So if we have sine is 0, sine is 1, 1 to 0, and then we can fill in the rest. This is 0.707. That gives you a kind of a head start, 0.5. Well, now you can easily see that this is 0.5, 0.866, 0.866. So just finding quick ways to fill in that chart is just really good. These are the things that you want to memorize. Now, what the hell is tangent again? Tangent of the angle is the sine part divided by the cosine part. So let's do it for 45. That's going to be, well, the sine divided by cosine. Well, that's going to be 1. Cool, that was easy. How about this? You know what I mean? Is going to be 0.5 divided by, that's where it's just like, hey, just call this 1. You know what I mean? So this is approximately 0.5. And then, hey, if this is 1 divided by 0.5, this is approximately 2. So you can kind of see how the tangent works. But we're going to have 0 divided by 1. Well, I guess we can still do that. That's 0. So we have 0, 0.5, 1, 2. But then what is 1 divided by 0? Well, that like goes to infinity. And so here's my other take-home point. Even when you get tangent, even though that we know tangent of 90 degrees, sorry about that, 90 degrees, goes to infinity. So if we have the tangent of like 89.9, that should be a pretty big number, right? I mean, if the tangent of 90 is infinity, tangent of 89.9 should be a pretty big number. Well, how about this? Here's a question for you. What's the tangent of 89? Because this is one that I would definitely remember. Because what we're saying here is like, are we going to, if we have any triangle where we're going to say, hey, the angle is just really, really tall. So here's that angle, and then this component's really small. This component's really big, so here's the sun shining. The angle is going to be about 89 degrees. And so the sun is shining. Here's the hypotenuse, is the bigger number. Like this is almost equal to the hypotenuse, and this looks pretty small, but I mean visually, I mean even it looks I mean if this is 100, how small does this be? You know what I mean? And I definitely have it not drawn to scale, but let's say that is 5, or let's say it's 2. You know what I mean? Or let's say it's even just 1. Are those pretty good guesses? I would say those are decent guesses. And what I'm getting at is when are you going to have an angle that's like less, like when are you going to have an angle that's like 89.5? You know what I mean? Won't 89, an angle of 89 degrees be your upper limit? You know what I mean? And what's the difference between, yeah, so that's all I'm getting at. So what is the tangent of 89? It's a good one to memorize. It's like 57. It's like 57. And it has nothing to do, I don't think it has anything to do with the radians being, like in our calculator, let's go to radians, and let's type in sine of, well, how do we actually get 1 radian? And what's the definition of a radian? So here's 1, and then we're going to have an arc length of, so if our radius is 1 and we have an arc length of 1 meter, radius is 1 meter, that's going to be theta. And so, and what's the circumference of this circle? Again, it's like circumference is 6 times that radius. It's about 6 meters, but it's 6.28 meters. It's 2 pi meters for that circumference of the circle. So what we're saying is, and what we're trying to find, I even forget what the hell we're trying to find, is the angle. So if we know that 360 degrees is 1 circle, what's the angle of 1 radian? You know what I mean? So if we know that 6.28 meters is 1 circle, and we're only going 1 meter of that, then we have a, so yeah, that's a good one where you're just like, that's all you need to know, and then you can just kind of, but no, these are good to figure out, because I can say that if I have a radius of 1 meter, the total circumference is 2 pi meters. It's 6.28. And then I can say, sure, if I had an if I had an angle that swept out 180, then but now we need to know the definition of a radian is going to there is 1 meter. You know what I mean? So we're going to have 1 meter over that 2 pi meters is going to be equivalent to our angle in radians divided by 360 degrees. So and I don't like doing factor label method this way, but what we're going to, like, I think the easiest thing to do is, like, what do we know? We know we have an arc length of 1 meter. And now we're going to, we want to divide meters by the meter, the circumference of a circle. So we're going to go 6.28 meters in 1, you know, like in 1 revolution. You can do it revolutions, and then 1 revolution is 360 degrees, or you can just do it in 1 step. That I have an arc length of 1 meter, and I'm going to divide that by the arc length of a full circle. That's 6.28 or 2 pi meters. Cool. And I'm going to say that's going to be equal to 360 degrees. So here is your factor label equivalent. 360 degrees is, I mean, for this circle of a radius of 1 meters, is going to be 2 pi meters. And okay, so and actually, yeah, no, this gives us the angle of 1 radian. Cool. So we have 360 divided by 2 pi. But this equation, you know what I mean? Even the fact that I just can't spit that out, it's a bizarre one. This is another one. Well, you'll graduate and then you'll just forget. You'll just be like, nah, I forget. I hate converting from degrees to radians. But yeah, so what I like to do, I guess, is just know that you do it by circumference. I don't know. I'm going to take a pause on that. I'm just surprised of how difficult that simple equation is to get to. So we have 360 divided by 2 pi, and hell yeah, we get 57.29, you know what I mean, 57 degrees. And so now what we're going to do is figure out what tangent of 89 was. So we'll just go back to degrees in our calculator. Tangent of 89, it's not the same. You know what I mean? Tangent of 89 degrees is 57 point, 289, you know, they're both 57.3. I find that's just a good target, you know what I mean? It's just something that they're not related at all. I mean, they might be weirdly, but, you know, a 1 radian is 57.3 degrees. You can remember that. And then what we're doing is we're trying to understand what tangent is. It's a number that goes from 0 to infinity, you know, and negative infinity, but we're just talking about geometric shapes. That's the idea of this video. Where your angles are just 0 to 90. 0 to 90 degrees for that shape of triangle. But yeah, you get this representation that tangent of 89 is 57. So it's nowhere near infinity, and that's a pretty good representation. So for whatever reason, I like to think of tangent as a number between 0 and kind of 0 to 60. 0, you know, you could do an acronym or just something easy to remember, like cars go 0 to 60. But tangent can go 0 to 60. And any number greater, any angle greater than 89.9 is just like, well, rethink the problem and be like, well, are you actually achieving that angle? Because yeah, it's just, you know, it's that I would be surprised what problems have you know, require kind of angles that are close to 90 that represent values of tangent to be greater than 57. But I could look those up and find that. But I would think that's a very small subset. Alright, heck yeah. If I don't think of anything else, we're going to do this little graph and probably cosine and the derivatives of the, you know, or the, you know, I don't know, yeah, the derivatives of them. Cause that, and then we'll go to that last problem of that cotangent, you know, that I said we were going to end with. So heck yeah. So why we did this in this equation. We said, hey, if the angle on sine is small, and I get the angle in radians, then the sine of that angle in radians is just that just that number in radians. And so that's why we kind of doubled down on what the hell a radian is. It's about 60 degrees. And this will work up to sine of 1 radian. You could say sine of 1 radian is 1. And it's not. It's close to 60 degrees, so sine of 1 radian is approximately 0.866. And we'll go back to radians. So we go sine of 1. Yeah, it's like 0.84. But just in general, like you can, even at this top end, you can just be like, and it comes back to this geometric shape, you know what I mean? But for angles between 0 to 30, it's like almost 100%. We're going to go sine of 0.5, and that's basically 0.5. And what does that say? That says, well, if we know that 60 degrees is 1 radian, 30 degrees, or 0.5 radians, I should say 0.5 radians, that angle is approximately 30 degrees. Now, it's approximate. But this means what we know from sine of 30, that's 0.5. So now we can say sine of 0.5 radians is 0.5. And we can see that assessment. Well, let's go to sine 15. And by this linear representation, we know sine of 15 is just, well, we know sine 30 is 0.5. So half that, we get 0.25. Well, that's sine of 15. So what is 15 degrees in radians? Well, we know that 60 degrees is 1 radian, and then we know that 0.5 radians is 30 degrees. So 15 degrees, just by visual representation, is 2.25 radians. Cool. And we know that sine of 0.25 in radians is going to be 0.25. So let's do it. Sine of 0.25 is getting more accurate. It's like 0.25. Sine of 0.1 is pretty much 0.1. Sine of 0.05 in radians is 0.05. So cool. And just know, you know, it's not a good guess to go from 30 to 60 with that, and it's called the small angle, you know, approximation. And it only works because you're representing this radius as that angle. You know what I mean? If you said this was the diameter and this angle over to here was 1 diameter, then no, it wouldn't work. You'd be off by a factor of 2. So if we had angles in diameters, you know what I mean? That's the thing why radians is such a bizarre one. What the hell is a radian? Well, take the radius and measured as a string and drape it around the circle, you get to there. That angle we're just classifying as 1 radians. You could do the same thing with diameter. You could take a string, measure the diameter of the circle, drape it around, you would get to there. And you would have an angle of 120 approximately. And what are you going to call that? 1 diameter? You know what I mean? It seems almost nonsensical. Your small angle theorem would be off by a factor of 2. But it's just cool when you use radiuses, your small angle theorem works really well. And I ain't, you know, that'd be a separate video. I don't even know like how to prove that or whatever. But okay, we're going to go back to this one. And so now that we understand radians, hell yeah, 0.5 radians. This is the degrees, and this is the value of sine. You know, this is that percent of a whole. And again, don't lose your mind, because what are we talking about? Heck yeah, we're talking about the sine, and that's going to be that percent of the hypotenuse. Cool. So we're going to go sine of 0.5. That's going to be 30 degrees, and we're going to get 50%, 0.5 of the hypotenuse. We're going to go to 60 degrees. And sure, we're only going to go up to 0.85, but like I said, you could just go up to 1 and call it a day. So like the real easy graphical representation of this is just go all the way up to there, and then you've already reached 100% and go to there. But we know this is 0.85, so look at this. But this doesn't change. This is always just right there. Then it slowly tapers off, and then it goes to 90. So there's the representation of sine, and it's obviously going to go back the other way and then repeat. But again, all we're interested in is the geometric relationship with that. So let me you know, now we can quickly draw that, because we have degrees in radians. And we're going to do 1, 2, 3. That's why we're going to do 3. We're going to go up to 1. We can go down to -1. And again, these are fractions of a whole. Think of this between 0 and 1%, or 0 to 1. This is 0.5. So this is 0.5 radians, 1 radian, and 1.5 radians. So if we go to 30 degrees, sine of 30 is 0.5. That's 50% representation of the hypotenuse. Sine of 1, well, we could say it's 1, you know what I mean, and then start there. But yeah, at the end of the day, this is our graph for sine, and obviously it's 0.866, so we're going to go there and go to there. Okay, so now, what is cosine? Well, isn't it just from what we've learned, like the exact opposite? So cosine is going to start at 1. When the radians is 0, we got 0.5, 1 radian, 1.5 radians. Obviously, now we know that this is 90 degrees. And don't think of it as pi divided by 2. I don't know. That'll just melt your mind. And so we're going to start at 1. And we're kind of going to do the same thing. Hey, maybe we go here, and then like what do we like? Hey, this is the graph of cosine of x, or cosine of the angle. So this is sine x, or just sine theta. You know what I mean? Cosine theta. Both these mean the same thing, and usually we're talking in radians. That's why we have this degrees in radians. So if we go out to 1 radian, which is that 60 degrees, and we have that in cosine. What's cosine of 60 degrees? I have no idea. So let's turn that into sine. That's going to be sine of 30. You know what I mean? And so sine of 30 is 0.5. So cool, right there. What's cosine of 90? Well, that's going to be 0. Cosine of 0 is 1. And so we're going to follow this backwards. And then even what's here? What's cosine of 30? I have no idea. But I do know that cosine of 30 is sine 60. So I'm going to go up to that 0.866. And I can do the same thing. I can call this 1 and be done, or I can say, hey, that's going to be totally accurate. Okay, so now I'm going to quickly go over, hey, this comes up a lot. What's the derivative? dx, sine x dx. Now, even derivatives, man, they suck. But all they mean is, hey, we're going to change this equation, sine x, by a little bit, and we're gonna change the x by a little bit, and we're gonna see if if this number changes a huge amount and this number just changed it a normal amount, well, then this is going to be the slope. We're going to have a hell of a slope. You know what I mean? And then if it's the opposite, if we change this number but nothing happens, but this number actually has a significant change, well, now our slope is 0. You know what I mean? So here, the angle is going to be real steep. Here is going to be 0. And then the only other one, hey, let's say there's a point where we change sine, and it changes by this number, and that's actually the same number that we changed the x value. So and that's what we have all through here. This is sine of 1. And so how do we do that? You know what I mean? So let's say, hey, we're gonna change x from 0 to 0.5 radians. Hey, it looks like we changed the downstairs part by 0.5 radians. And then the upstairs part, what did it change? The upstairs part, the actual function, it went from 0 to 0.5. That's that percentage of the whole. So now we have 0.5, and now we have 0.5 divided by 0.5. That's a slope of 1. And that's what we see all through this region. And if you extrapolate, who cares? All the way up to 60. That's a small angle theorem, really going big, all the way up to 60 degrees. Now, if we go over here, you can do this in your calculator. You throw in cosine of and we'll do this in degrees. So you throw in cosine 0 degrees, you get 1. You throw in cosine 1 degree, you're going to get 0.999. And that's another good check mark on reality. Let's do that. You have to be in degrees, but we're going to go cosine of 1. Holy Toledo, it's 0.999. And then finally an 8. So that's a good one to know. Like, we changed by 1 degree, which is significant, but we only went down in this equation, and we went down, so that's a negative, and we went down by like 0.00. I can't even do it, but is it 2 thousandths? 1 minus that? Yeah, it's 1, 2, 3, 4, and it's even 0, 3 zeros and a 0.15. That's crazy. So hardly changed at all. That's why the slope of that line is 0. Now, technically, that's not going to be the easiest way or the fastest way to remember that the derivative of cosine x is, what do we know about it? Well, we know that right off the bat, it's 0. Like, you have 0 slope, but then slightly negative. You know what I mean? So we need something that when you throw in 0, we get 0. And then when you throw in a small value bigger than 0, you get something negative. You got to do 2 things for that one. So let's talk about the derivative of sine. So the derivative of sine means that we're getting when we do the derivative of sine x dx, and we throw in 0. You know what I mean? We are seeing a slope of 1. At that point, the slope is 1. So when we throw in x is equal to 0 degrees, radians or degrees, we get a slope of 1. So it's like, hey, what equation when we throw in 0 is 1? Well, that's cosine. So cosine of 0 gives us 1. So that's just think, hey, cosine of 0 is an equation that gives you 1. And it gives you, and then so that's the sine part. So if I want to know the derivative of sine x, I just think, hey, I know my slope is 1 because it looks like that. What gives me 1? Well, cosine gives me 1. If I want to find the derivative of cosine x dx, well, I know that this starts at 0, so if I throw in, like, isn't sine 0, 0? Cool, yeah, but then you just have to know that this goes negative. You know, it starts at 1 and goes negative, so it's just negative. So the derivative of cosine x dx is going to be negative sine x. There's 2 things going on here. One, it's going to be negative, and then obviously, your slope is going to be 0. So sine x, when you throw in 0 degrees, you get that 0 slope right there. All right, hell yeah. Alright, I think I need to get on with my day, so we're just going to do one more thing. This comes from material mechanics. We're going to have a bar out here, and we're going to have it attached at a wall, and we're going to have pivot points. And so, heck yeah, we want to know and I'm just going to say this is the reaction. It's the force inside this cable, and then we're going to pull down with a P. We have an angle here, and in general, the foreshadow, this gets us a relationship of cotangent theta, which is 1 over tangent theta, which I just want to say is, hell yeah, that's just sine theta divided by cosine theta. Okay, so how do we do this? Well, we need to, the easiest thing to do is like, hey, we have a reaction pin over here at A, so we're going to have an AY and an AX. Do we know what those are? Do we care? No, because we're going to take moments about that point. It's a statics problem, and so moments about that point are going to be 0, and what that means is that if this causes a torque that way, it has to be balanced by this torque that way. And because if we take this whole thing and do, like we're doing, a free body diagram, we're going to take it, chop it out of outer space, put it in deep space, and if we apply these forces, hey, it's still going to remain stationary in outer space. And I just find that very fascinating. You know what I mean? So yeah, some of the moments about A is going to be 0, and that brings up, well, the moments about any point is going to be 0. So you could take that stationary object, throw a thumbtack in it into outer space, and it's still not going to rotate around that thumbtack. So that's where the sum of the moments are 0, but that means that about every point, and I find that very fascinating. Cool, so if we do that, we're going to have a torque. This is the length of a bar. We're going to have a downward torque, so we're going to have a negative LP, and then we're going to have an upward reaction of R. Hell yeah, let's use our skills. Here's the sine of the angle, so we're going to have an RY up, and then a component RX that direction. So we say that this Rx is going through the pivot. It's like opening a door. You can't open a door by pushing on the pivot. You have to go out and then push on the door at a perpendicular. So only the perpendicular component is what's causing a torque from that reaction. So sweet. So it's going to be a positive torque, and it's going to be this Ry. But we know what this is. It's the sine. This component is the sine component of the bigger part, the hypotenuse. So we're going to say, hey, we're going to take that bigger number and then multiply it by that fractional component, that sine theta. Cool. And and then times the distance. So sorry. So it's going to be, I'll just throw the L right there. Usually you put the force first, force times distance, but whatever. So that's going to equal 0. Okay, so sweet. So now we can actually solve for our, what do we want to solve for? Like R or P? I forget. No, we want to solve for this reaction. So let's do that. So we're going to bring that to that side. We're going to go R. LR sine theta is equal to LP. The L's drop out, and we're going to have R is equal to P divided by sine theta. So cool. We have our first representation of what this reaction is. I forget what we wanted to do with this problem. But now we're going to sum the forces in the Y. For whatever reason, okay, so sometimes you just have to do everything. That's what I do. So actually we're going to sum the forces in the X. So we just have this AX and this R, so we're going to have is equal to 0. So we're going to have AX is equal to, but it's just the cosine component of R. So we're going to have equal to R cosine theta. And instead of, I just said they're equal to, but if we said the sum of the forces are equal to 0, obviously this AY is positive, or this AX is in the positive direction, and then we're subtracting this R cosine theta component, the component that's going in that direction. And that's going to equal 0. I actually have to take a pause of what the hell was I even getting at where you got something that's 1 over cosine. So apologize. Okay, yeah, I'm back. That just took me 2 minutes. I totally forgot like what problem was I actually trying to solve. It was a material mechanics problem where hell yeah, this is like, hey, a piece of steel and it's pinned, but we're putting a force into it. You know what I mean? We're actually putting a force. We want to know that reaction force. And basically this is the AX. Whatever AX is feeling is the force in that member. And then so if we have a compression force of a piece of steel, you know what I mean, in compression, then we can find, you know, the surface area of it, what kind of tubing we need to actually support that load. So that's what we're doing. So we're actually just trying to find this reaction at x, and that's going to be representative of what that beam feels. So we're going to go AX is equal to R cosine theta, but now we want to know what R is in terms of P. So that's what we do. So sweet, we take this R term and then throw it right in there. So sweet, we have this reaction at A, which is representative of the force and compression of the beam. So I might just say FC of that beam that we're analyzing for this problem, and that's going to be equal to, well, this so this P sine theta goes right there, and the cosine theta is on top. So it's going to be P cosine theta divided by sine theta. Now this is our answer, and you know, since this was an introduction into trigonometry, hell yeah, we know exactly what's going on. If we see a sine and cosine, we obviously know where those came from. But now we can use the fact that tangent theta is equal to sine theta. It doesn't help the problem, you know, to me, or I mean, divided by cosine. So tangent is sine divided by cosine. And then we can see that this is sine down here and cosine up top. So we obviously know that 1 divided by tangent theta is cosine theta divided by sine theta. Or you can just say, hey, look at this. Tangent theta is equal to sine theta divided by cosine. I see the sine and I see the cosine in the opposite. So I can just easily see that this is P divided by tangent theta. So see how I did that? Or you could get this representation, cosine divided by sine, that's what I see, and that's 1 divided by tangent. That's going to be P times 1 divided by tangent, that's what we get. But we also know that 1 divided by tangent theta is also cotangent theta. So we can say that the force in compression of the beam is that reaction AX, which is P cotangent theta. You know what I mean? So there you go. If you saw that in a textbook, I would just say, nah, thanks. But at least I know where it comes from. And I could be like, well, at least 1 over tangent theta. I have a button on my calculator for that. You know what I mean? I don't have a button on my calculator for cotangent theta. And I just like the fact that you can turn that into cosine, sine theta, cosine theta, and obviously we know where these terms are coming from. So there you go. So there's my introduction to trigonometry. I think those are the basics things. I'm sure I missed, I'm sure I'd want to spend another, 3 hours going over kind of basic stuff that I really enjoy. But that's it. I'm pretty proud of this one because dang, that was kind of all my tricks all in one video. There was only a couple places where it got just a little bit crazy, but that's all right. And so heck yeah. So thanks for joining me. And guess what? That's a video.